Good evening, chemistry nerds. This is the Matter and Energy Practice Exam video where I'm going to go over the 30 questions on this practice test in preparation for your test on Thursday for the Matter and Energy unit. So this encompasses everything going all the way back to matter, pure substances, mixtures, all the way to heat calculations and heating and cooling curves. So there's a lot in this. We suddenly go into talking about what the heck is matter to now calculating and doing math in chemistry all of a sudden. But anyway, let's get yourselves relaxed. I'm pretty relaxed right now, laying back on my couch, watching some Netflix, pulling up Cinderella Story, because yes, I am a sucker for cheesy rom-coms. What a throwback movie. But anyway, let's get ourselves started. Make sure you have your reference table out, because you're going to be needing that for some equations. So let me pull that up in a bit. Well, actually, for number one, we don't really need the reference table, because we're going to look at this heating curve right here. So the graph below represents the heating curve of a substance that starts as a solid below its freezing point. So if we look at the start of our graph right here, this is our solid phase, and then we're heating it up over time until it probably reaches the gas phase over here. And the question is asking, what is the freezing point of this substance? Look at that, what a typo. What is the freezing point? Okay, so freezing point meaning we are looking at the part where a temperature, we're looking for a temperature specifically where it freezes, goes between solid and liquid phases. It's the same as calling it the melting point. They're both temperatures to represent the transition between solid and liquid phases. So let me go ahead and label this. In our graph here, we start as the solid, so I'm going to put an S for solid. Well, that's not a really good color. Let's make it darker. So that's an S for solid. Here's a liquid, and here's a gas. In these flat lines, that's where you're going to see them transition between those phases. So here is between solid to liquid, and here is liquid to gas. Phase changes occur when the temperature is constant. So here, when temperature is constant, it's these flat lines. It stays the same temperature over time. So we're looking for the phase change, freezing point, or melting point between solid and liquid. So it's going to be right over here. We're going to look and extrapolate over here to the temperature side, because we're looking for a temperature. And that is about, that's less than 60 degrees, but it's more than 30. So if we look at our choices, it's got to be choice 2. Okay? Now number 2. Differences in which property allow the separation of a sample of sand and seawater by filtration. Okay, so separation methods take advantage of certain physical properties. So think about appearance, size, shape, etc. So we're thinking about what filtration does. Filtration separates based on particle size. So when thinking about filtration, you're going to think particle size. So bigger particles get trapped, while smaller particles can go through the filter. And so that's choice 4. Number 3, at standard pressure, so we can ignore that phrase, we don't need that right now. During which physical change does the potential energy decrease? So physical change, we gotta think phase changes, because they're also the same. Does the potential energy decrease? So if we look at our case right up here, heating curves show potential energy increase. So here we could see that kind of intuitively, everything goes up, energy goes up. Now the opposite direction, cooling curves, things go down. So I'm going to specify here cooling processes where you have a cooling curve like this. That's where potential energy goes down. Both potential and kinetic energy go down in general. So we're looking for something that sounds like a cooling type process, or I guess physical change. And so looking at each of these, we're going from a gas all the way down to a solid. So we're moving away from the gas and going towards the solid. And looking at each of our choices, that's got to be choice 2. Going towards a solid from a gas or a liquid. Alright, number 4. What is the minimum amount of heat required to completely melt 20 grams of ice at its melting point? So we're looking for numbers here. So that means we're going to calculate. So it means we need to pull out our reference table for a bit. Okay, So when it comes to calculations and equations, you're going to look at all the way to the back. That's table T. And in our heat section, we are looking for something to calculate heat to melt ice at its melting point. So looking at our three equations, there are only three of them, but they each have different purposes. The first one, MCAT, deals with temperature change. This one with HF, heat of fusion, is between solid and liquid phases. HV, vaporization, is between liquid and gas phases. So since we're dealing with melting, that's solid and liquid. So we're going to use the middle one, HF. Q equals MHF. Now what is Q? That's heat. So we need to calculate for Q. We need to make sure we have mass and HF. And looking at our substance, the key word here is ice. So we're dealing with H2O. So let me just first write down our equation for now. Let me get rid of this guy. Let me pause for a minute. Okay, so I pulled out table B. This is directly on the front page of the reference table, and this has the physical constants for water. So our equation is Q equals MHF. If you use capital Q or lowercase q, it's the same thing. That's alright. So we need to find Q. In our problem, they give us the mass of 20 grams. Remember that grams is a mass. That's a unit for mass. So 20 grams times HF. That's heat of fusion. These values work if our substance is water. If our substance is not H2O or water, then we have to use something else, or they give it to us, or we have to solve for it. So you gotta make sure you look out for those keywords. If they don't give it to you, it's probably you have to solve it, or it's water. So right here, ice, we're gonna use this value, 334, for our HF value. Don't worry about units too much. 20 times 334, that is going to be this many joules. Okay. And look at that, that's our answer choice C. So that's number 4, and we're already 7 minutes in. This is going to be a long one, guys. Don't worry, it's only 25 questions on the test. Okay. Number 5. When 420 joules of heat energy, so now that's our Q value, is added to 10 grams of water at 20 degrees Celsius, the final temperature. So now we're dealing with temperature change. So that means we got to use this equation. Q equals MC delta T. That's our equation, MCAT. So it's because we're dealing with temperature changes here. So they're giving us 420 joules of heat. Okay, 10 grams is our mass. Water is our substance. So looking back at table B, we can see that we're looking at C. That's specific heat capacity. That's C. So we're looking at this guy, 4.18. So we're going to plug in 4.18 for C. And delta T, that's our temperature change. So let's solve for that right now. Okay. So delta T, you should get, is 10 degrees Celsius. That's a change though. That's final minus initial. So that means our original is at 20. That means we changed by 10 degrees. That means we got 10 degrees hotter. So you could do some math or reason it this way. If our change, we increased by 10 degrees and we started at 20, that means our new temperature has to be 30. And that's how you do that. This one's tricky, so be careful with these. Okay, number 6. Object A at 40 degrees Celsius and object B at 80 degrees Celsius are placed in contact with each other. Which statement describes the heat flow between objects? This is kind of simple. Just know that heat flows from hot to cold, or high temperature to low temperature. That's another way to think about it. So whichever one is the highest, that's object B, because it's higher number, it's going to go from B to A. Choice 2. Okay. Number 7. In which process does a solid change directly into a vapor? So this one's tricky. Usually we go solid to liquid to gas in that order. But there is a phase change that bypasses the liquid phase. You could go between solid and gas, or gas to solid. Okay. This one, I always like to think of it in terms of the heating curve. you know? Gas is here, solid is down here. So we're moving our way all the way up. That's called sublimation. The other one, in the opposite direction, is called deposition. So that's like depositing down, but sublimation, you're sublime, kind of going all the way up. Thinking of something that's sublime, it's at a higher state. So you're going from solid to gas. Gas is a higher state. That's how I perceive it. Okay. So that's choice 2. Number 8. Which phase change is exothermic? So this kind of requires us to remember some of the key words here. So exothermic means to release heat. Another way to think about it, you're getting colder. Okay, so getting colder. So that means we're going from gas to liquid to solid. So we gotta think of which phase changes moves us away from gas, going towards solid. So that means we gotta look at these. We gotta look at these little symbols. They represent the phases. So anything that goes towards the solid phase is always a safe bet. And right here, choice 2 is our answer. The rest of them go in the opposite direction. Okay. Number 9. Now we got another heating curve. Okay. Which statement correctly describes the energy of the particles of the sample during interval BC? Okay, so we need to think about energy. First, we got to remind ourselves that kinetic energy is the same as temperature. Okay. So during BC, temperature is staying constant. If temp is constant, so is the kinetic energy. So we could cross off these choices. We could cross off choice 1 and choice 4. So that means we're left with 2 and 3 because they have kinetic energy remaining the same. Now taking a look at here at our heating curve, we're going up. So when it comes to potential energy, it kind of follows in the same direction as kinetic. So with raising temperatures, you also have a rise in potential energy here. Not necessarily with raising temperatures, but in our heating curves, potential energy goes up as well. Okay. So heating curves show potential energy and kinetic energy going up together. Not necessarily going up together in the same segments, but one goes up, the other's constant in each segment. So here, it's got to be choice 3, not decrease. Alright, number 10. What is the total number of joules released when a 5-gram sample of water changes from liquid to solid at 0 degrees Celsius? Okay. Let's first identify what we have. We got 5 grams. That's a mass. So we got that M is equal to 5 grams. Our sample is water. We are looking for total number of joules. So joules refers to heat. So Q is our question mark. Okay. And we're going between liquid and solid. So that means we are changing phases here. Liquid and solid, that's fusion, not vaporization. So that means we gotta look at table B for the HF value. So just double check, heat of fusion, HF is going to be (334 joules per gram). Okay. Sorry, my app is being weird. Okay. So that means we're going to use Q equals MHF. Plug in your values. We're looking for Q. So 5 times 334 5 times 334 is going to get us somewhere over 1,000, definitely below 2,000. You get somewhere around Q equals 1670 joules, and that's choice 2. Okay. Number 11. Which form of energy is associated with the random motion of particles in a gas? So we're going to think motion. So that's like kinetic energy. Kinetic energy deals with temperature. Temperature deals with heat. So if we look at our choices, definitely we can eliminate some of them, nuclear, electrical. So some of you might be stuck between thermal and chemical. Whichever one sounds like kinetic energy and heat, you're going to pretty much go with choice 4, thermal. And that's our answer for number 11. Okay, number 12. Which temperature represents the highest average kinetic energy of the particles in a sample of matter? So when we look at this, we're thinking, what's highest average kinetic energy? So kinetic energy is the same as temperature. Okay, so we're looking for the choice with the highest temperature value. Now, looking at our choices, it's a mix of degrees Celsius and Kelvin. So we need to make sure we convert them to the same unit, because 27 degrees Celsius is not the same as 27 Kelvin. They're going to be two different numbers, alright? So we're going to look at our reference table all the way in the back, and you're going to pull out that equation, and I'm going to write it for you guys right here. So Kelvin is equal to degrees Celsius plus 273. So looking at your temperatures, we're going to look at choice 3 and 4. We're going to take these numbers, add 273 to turn them into Kelvin. Okay, so here, 27 plus 273. Okay, so that's going to be about 300 Kelvin. Okay. And choice 4, 12 degrees Celsius, add 273. That is going to be 285 Kelvin. So looking at now that they're all in Kelvin, we're going to see the one with the highest temperature, and that's choice 3. Okay? So we could see there that degrees Celsius and Kelvin are two different units. So make sure you convert them all to the same unit so you don't get confused. So that's the strategy here with these. If you see different units, just convert them all to the same one. Kelvin is easy, just add 273. Okay, number 13. Here we have another heating curve of a solid going all the way to gas. Now the question is asking which statement describes the energy of the particles in the sample during interval CD. So we're going to look at interval CD right here. So that's our segment. Let me highlight that. Okay, alright. So that means we're seeing temperatures rising. So if temperature rises, that means kinetic energy also rises here. So if, for number 13, if temperature goes up, so does the kinetic energy. Now, here's another thing to remember. One goes up, the other energy stays constant. So because kinetic energy is rising, that means potential energy has to stay constant, and vice versa. So like during these segments, potential energy will be changing, but kinetic energy is constant. So you're never going to have both of them changing together. One changes, the other's constant. And that's always the case in every segment. They just trade on and off. Which one rises, which one's constant. Okay? So here, if we look at our answer choices, they don't both change. So we can cross off 1 and 2. They're both not changing here. One of them changes, the other is the same. Now, the one that matches what we're looking for, that's choice 4. Potential energy remains the same, but average kinetic energy increases, just as we saw there. Okay. Number 14. Let's look to the other side of this page. We got a particle diagram, and we're looking for the one that represents one substance in the gas phase. So if we look at our choices, let's eliminate some obvious ones. Choice 2 and 4 show solid phase. How do we know where they're in solid phase? That's because they're stuck together. Looking at choice 1 and 3, they're free particles that are floating around. So that shows gas phases. But now it's the difference of which one shows only one substance. Okay? So if we look at 1, we see 2 different colored atoms. So there's 2 different elements. So gas of 2 substances. And then choice 3 is a gas of only one substance. because it's one color. So make sure you're able to interpret these correctly. Okay. Number 15. When KCl solid is dissolved in water, the resulting solution is classified as what? Okay. So looking at this, we have KCl, that's a salt going into water. So basically we're seeing when something's dissolved in water, that's an aqueous solution. That's also a salt-water mixture. So we already know this is a mixture because we're mixing in two things together, two different substances. So it's not a compound, we're not chemically combining them. Now, homogeneous versus heterogeneous. These things are always homogeneous because they're evenly mixed. Okay, so this is always a homogeneous mixture. Aqueous solutions, saltwater mixtures, all these things are always homogeneous because you can mix them up evenly that way. Okay, number 16. Which sample of ethanol has particles with the highest average kinetic energy? So highest average kinetic energy again relates to highest temperature. So thankfully they're all in Celsius, degrees Celsius, so we could just look at the highest temperature number. And that's choice 2. 10 milliliters of ethanol at 55 degrees Celsius. This doesn't matter about the volume of ethanol. All that matters is the temperature. That's what we're looking for. And that's all we need. Forget the mLs. Alright, number 17 here. We are looking for the amount of energy required to vaporize. Okay, so we're looking for how much energy. That means Q is our question mark. To vaporize, that means we're going between liquid and gas phases. So we're going to use HV. 10 grams of water at its boiling point. So our mass here is 10 grams. Since we're doing heat of vaporization, HV, we gotta look up on the reference table. Okay, now HV, heat of vaporization, is gonna be this number. Keep in mind we're still dealing with water, so that's why we're looking at table B for these numbers. Heat of vaporization is 2,260 joules per gram. So we're gonna use that number. Okay, 60 joules per gram. Okay, so let's calculate this. Q equals mHV. So Q, we're looking for Q. So we're just going to multiply 10 with 2,260, and we get 22,600 joules. Now looking at our answer choices, they have to be in kilojoules. Going from regular joules to kilo means we're just going to move this decimal point over 3 places. So it's going to equal 22.6 kilojoules. Kilo stands for 1,000, basically. So 22.6 kilojoules means 22,600 joules. Okay, that's choice 4. Number 18. An example of a heterogeneous mixture is... So let's look at our answer choices. I don't know what I'm saying. I can't English. Okay. Number 1, soil. Number 2, sugar. Number 3, carbon monoxide. And number 4, carbon dioxide. So choice 3 and 4 definitely sound like compounds. Those are not mixtures. Neither is sugar. Sugar is also a compound, like glucose, C6H12O6. Brain fart there. So that leaves us with soil. Soil is composed of different substances here and there, not just, it could all be different elements, different carbon compounds, etc. Organic matter. So soil is a mixture, it's heterogeneous. Every time you reach your hand into a clump of soil, does it always look the same? Is it mixed the same way? Never. So that's why it's heterogeneous, it's unevenly mixed. Every time you reach your hand in, does the clump of soil look the same each time? No. That's what makes it heterogeneous. Homogeneous, on the other hand, would be it looks the same all the time each time you take your hand out to take a sample. But anyway. Number 19. Which two particle diagrams represent mixtures of diatomic elements? So diatomic meaning two elements. Sorry, not two elements, two atoms of the same element. of same element. Okay. So that means we need to see two black dots together, like this. And two white dots together, like that. So we need to see a mixture also. That means we need to see mixtures, a diagram that represents both of these. So mixtures of both. Diagram A follows through, and so does diagram C. Looking at diagram B, you see here, that's a compound of A and B. I mean, not A and B. Element 1 and element 2. Choice D also has compounds mixing the black and white together. We need to see just like A and C. And that's choice 2. Okay. Oh wow, someone just fell off the diving board in the movie. I digress. Number 20. A 10-gram sample of H2O liquid at 23 degrees Celsius absorbs 209 joules of heat. What is the final temperature of this H2O sample? So this is a tricky one, so be careful with this. So here we are looking at 10-gram sample. So that's M. Absorbs this much joules of heat. So Q is given to us. Equals 209 joules. Okay. What is the final temperature? It starts at 23 degrees Celsius. Okay. Our sample is also water. So looking here, we're having a temperature change. Specific heat capacity, so we're going to use this one. MCAT. Okay. Q equals MC delta T. That's because we're dealing with temperature change once again. Okay. We have 209 as our Q. 10 is our mass. C, we have to look at table B. That's 4.18. Delta T is what we need to figure out for our final temperature. Okay, so plug and chug, do a quick calculation. Okay, so delta T is then 5 degrees Celsius. So if you calculate for delta T, the temperature difference, it's 5 degrees. That means we changed our temperature by 5 degrees. We started at 23. If we're absorbing heat, that means we're getting hotter. So that means we have to raise our temperature up by 5 degrees. So our new temperature is 28 degrees Celsius. Okay. Number 21. When 10 grams of a compound was dissolved in 100 grams of water, the temperature of the water rose from 25 to 30. For each gram of compound dissolved, how many joules of heat were absorbed by the water? This sounds like a lot. Okay, so let's break this down. Alright, so first let me pause to think about this one. Okay, so we need to read this question carefully, so I can't stress enough how important it is to read each question carefully. Annotate it in case you get stuck in a question. Okay? Because these things can get very wordy, and it's hard to interpret if you're not careful. Okay, so they give us two masses. So which one do we use? Compound, mysterious compound, or the water? If you're really stuck, I would probably go with the water because that's the one we've been dealing with all this time, and it's easier to use. But here's the reason why. Each gram of compound dissolved, how many joules of heat were absorbed by the water? So we're focusing on the water here. Heat absorbed by the water. Okay, so we are looking for Q. In this space, I'm going to do number 21. So Q is a question mark because we are looking for that. The temperature of the water changed from 25 to 30. So that means our delta T is 5 degrees Celsius. We changed it by 5. The mass of the water is 100 grams. And since we're dealing with temperature change, we're using MCAT again. So that means we need to use our C value of 4.18. Okay. So Q equals 100 times 4.18 times 5. Multiply those three together and you should get your answer. Okay. Okay, so our Q value is 2090 joules. Now if you look at your answer choices, it's none of these. Because now that I remember, this was a test question last year, and this was a mistake here. None of these answers are correct, because these answer choices were changed from the original form. So, if you did this correctly, you should get 2090 joules. You're not crazy, you are correct. Okay. So do not fret, this is the real answer. None of those answer choices are correct. Okay, number 22. The temperature of a substance is a measure of, so as we looked in the previous questions before, we relate average kinetic energy with temperature. So that's what those questions are talking about. So make sure you remember that. Temperature is a measure of average kinetic energy of the particles, choice 1. Okay. Okay, so here we have a data table, a graph, and we have to do some stuff with this data table and the graph. Okay. Number 23, the heat of fusion for this substance. That means we're not dealing with water. They give it to us. So HF is equal to 122 joules per gram. How many joules of heat are needed to melt 7.5 grams? So we have a mass of 7.5 grams. And we're looking for joules of heat, so that's Q. So we're using this equation, Q equals MHF. We're solving for Q. Q equals 7.5 times 122. Multiply them together to get your answer. 7.5 times, times 122. You get 915 joules. That's your answer for number 23. Okay. Number 24. What is the evidence that the average kinetic energy of the particles is increasing during the first 3 minutes? Okay. So during the first 3 minutes, we have to look at our data table. From 0 to 3, what is happening to the temperature? It's rising. So because the temperature is rising, so is the average kinetic energy. So our answer, we're going to state here, is because temperature is rising. You don't have to say any more. You can elaborate a little bit on the relationship between temperature and kinetic energy, but that's all you need to state. Why is kinetic energy rising? Because temperature is also rising. And that's it. Number 25, we gotta plot the data from the data table, circle and connect the points. If, let's say, we have a question like this on the test, I better not see empty questions. Y'all all should know how to graph. Kiddos, you learned this in math class. Okay, so let's make sure we know how to graph properly. So plot the data from the data table, circle and connect the points. So let's see. I'm going to pause for a moment to show you the entire plot, but you should also take this pause moment to do the graph yourself as well. So play again. Take a look here. This is what your axes should look like about, just so you can properly plot these. Now here's another pause so I can actually plot them. Okay, so number 25 should look like this. So you gotta make sure you plot each point, circle them, and connect them with the line. So I circled them in blue, plotted them in green, and connected them in red. So this is what your graph should look like to get the full point for this question. And finally, the last question, number 26. Based on this data table, what is the melting point? So we're looking for a temperature, okay, that shows where it's melting. And remember, during phase changes, melting and freezing, evaporating, condensation, we are looking for a constant temperature. So right here is where the temperature stayed the same, and you can also see it on the graph here as well. And that is 53 degrees Celsius. You don't have to explain anything, but I'm going to write an explanation here. Because temperature is constant. And that is the end of this practice exam review video. If you're stuck on some things, feel free to come to the review session, or feel free to watch some content related videos. Just search up matter and energy somewhere in this YouTube channel. But anyway, best of luck, guys. You know, just make sure you do your job well. Just make sure you review everything. if you review all the important words, phrases, definitions, keywords, and how to do some calculations, know how to use the reference table, I think you should be a-okay. Alright, enough talking from me. Good night, guys.